Alright, hi Year 12s, this is Mr. Lim here, and this is our last video on changes to volume for equilibrium systems, and let's get started. We're going to be learning about how to graph them and what kind of considerations we need to do, especially drawing stuff to scale. Alright, so graphing changes. First of all, we need to remember that there are two types of graphs. There are the rate of reaction graphs and the concentration graphs, and so we're going to start with the rates of reaction graphs. Okay, rates of reaction graphs, ooh, blue. Remember that when you have a change in volume, that both rates of reaction will go up or down, depending on whether you've got a volume increase or volume decrease. Okay, so remember both rates of reaction will do so. However, then you need to think about which reaction makes less particles, will spike up or down more than the other. Right, so that means you have to go back and count how many particles there are on either side, and so therefore say, okay, well, that one spiked up more, that one spikes up less than the other. All right, so then the rates of reaction will move together until equilibrium has been reestablished. Okay, so that's just the same as all the others. Okay, so let's have a look here. Here we can see that here's the rate of reaction graph. Here's the forward and reverse rate of reactions started equal. Okay, and then something happened. All right, both forward and reverse rates of reaction, they decreased. What kind of volume change causes the both forward and reverse rate of reaction to decrease? That's a volume increase. Make more space, they'll collide less often, and therefore they will both decrease in rate of reaction. What we notice is that the forward rate of reaction decreases more than reverse rate of reaction, which means that forward rate of reaction must make less particles. Does that make sense? Because we just said the reaction that makes less particles is the one that is more affected by the reaction that makes less particles will be more affected, will spike up and down more than the other. So the forward reaction must make less particles. And if we have over here, this is part of that reaction. The forward reaction must make less particles, so the coefficient here must be a value higher than 3. So I don't know, it could be 5 something, could be 6, could be whatever, right? But the idea is that, well, actually, it can't be 6. Who can tell me why it can't be 6? Because then it would simplify to 1 to 2. So, yep, some number that's not divisible by 3 has to be that number. All right, so as long as it's making less particles in the forward rate of reaction, then that statement becomes true. All right, so that's how you would graph it. The double spike, all right? One spikes up more and less than the other, and then remember to use your rulers to draw all the straight line parts. Okay, let's move on. Okay, so when you're graphing changes in concentration this time, okay, concentration graphs, not rate of reaction graphs, there are a whole bunch different, all right? Because then you really need to start thinking about making everything to scale. Okay, so these are the important things. All concentrations will initially change by absolute amounts, not stoichiometric amounts. Absolute amounts, not stoichiometric amounts. What does that mean? That if you've doubled the volume, you halve the concentrations, which means that a 1 mole will go to 0.5 mole or a 2 mole will go to 1 mole, which means that the changes are going to be different and they're not going to follow stoichiometry. Right, so you really have to read the question carefully to say, okay, well, did the volume increase? Did the volume decrease? Did the volume halve? Did the volume double? It's generally double and half because it makes it easier to work through. And I have seen some questions where they don't graph it accurately like this, but you should still try. But you just have a look at what you need to do. Okay, then after the initial spike, after it, the net rate of reaction will determine which concentrations will go up or down. Okay, so that means you have to go back to your equation and you say, okay, well, which one is making more or less particles? Therefore, that one increased more or less, and that one, therefore, will be favored, and that reaction will be occurring more or less than the other. All right, so you need to go right back to all of that collision theory stuff to work out what the net reaction is going to do. Okay, And then after the initial spike again, the changes in concentration will be stoichiometric. Right, so how is this different to the sentence before? This is this part here, this sentence here is which direction it will move, up or down. And this sentence here is by how much. So you need to work out the net reaction to work out, okay, well then those ones go up, those ones go down. Then you need to look at the stoichiometry, the values, to work out, okay, that one goes up by this much, that one goes down by that much. All right, dynamic equilibrium is reestablished, and then, the concentrations cease to change. So let's have a look at this equation here. All right, so I have A gas, B gas, C gas, and D liquid. All right, so you see here that we do not include this because it's a liquid. So we say, okay, how many particles are on either side? 1 and 3, which makes 4, and 2, which makes 2, which means that this way makes less particles and this way makes more particles. Okay, so with whatever happens, the forward rate of reaction is going to be affected more than the reverse rate of reaction. Right, so let's have a look. We can see here that the volume decreased at this time. The volume decrease means that the concentration will increase because you're squeezing it together, you're going to make them more closer together. So they're all going to go up by absolute amounts. So this B here is at 1, 2, 3, 4, 5, 6. This is at 0.6, which means that it will go to 1.2 because it will going to double. I'm just going to say that the volume is halved. So it's going to go to 1.2, which means it goes all the way up to here, which means it spikes up to this much here. Okay, this is just the initial spike. This one is at 0.4, which means that this has to go to 0.8, which is about here. So that one goes up, whoops, nope. That one goes up to about that much. And this is 0.2, which means it will go up to 0.4, which means it ends up here, which is about there. Okay, so that's just the initial spike. Now we have to work out which direction is it going to favor. So the volume decrease leads to an increase in rate of reaction. Okay, so both rates of reaction are going to increase. Both rates of reaction are going to increase. Which one's going to increase more? The one that produces less particles. So the forward rate of reaction increases more than the reverse rate of reaction, which means that there's a net forward rate of reaction, which means that the forward rate of reaction is favored. Okay, if the forward rate of reaction is favored, that means C is going to go up and B and A are going to go down. B and A are going to go down. Okay, so that's worked out which direction it's going to move in. But now we have to work out by how much. So let's just say for B, it's going to go down by, B, it's going to go down by, let's just say 3 because that's a nice number. 1, 2, 3 here. Okay, so that's a drop of this much. Okay, which means it will end up round. Okay, let's just use a ruler because we need to make this nice and beautiful. Let's say it ends up about here. Okay, and I'll draw my curve to that point, and I'll flatten it after that point with my ruler. Okay, so that is how much B changed by. It changed by 0.3. Okay, A is going to change by 0.1, which means it's going to go from 0.4 to 0.3, which means that it should end up around about here-ish. Okay, so you can draw that curve there and continue that one on. And C is going to go up by 2 or 0.2. So 0.2 up from there is approximately here, and therefore it's going to end up there-ish. Okay, and then you just draw your dot and your line to there, and then you draw your straight line onwards from there. Okay, and so that's how you would draw that particular concentration graph for a change in volume for a gaseous system there. Okay, so really important that you can do this stuff, because if you can't do that stuff there from this here, therefore you can't draw that graph. Okay. Okay, let's have a look then. You can actually just use ones that have been drawn before to give you information about it. Okay, so the initial spike can tell you the volume change, whether it was up or down. Then you can work out the number of gaseous particles on either side by which side was favored, right? So let's have a look at something that was built here before. Here I have two substances, A and B. This is a concentration graph, and A and B were both dropped in their concentration. That means that the volume must have done what? The volume must have increased. Okay, the volume increased, and we can see that this one, they both halved, because this is at 0.7, it's gone to about 0.35, and that's gone from 0.6 to 0.3. Okay, so the volume doubled. That's just information from that spike. Oops. From that spike. Now, once we've got that information about the spike, we have a look at it and we say, okay, well, we should recognize that B went up and A went down. And if B went up and A went down, that means that the forward rate of reaction is going faster than the reverse rate of reaction over that period of time. Okay? So therefore, the forward rate of reaction is favored. The forward rate of reaction is greater than the reverse rate of reaction, or if there's a net forward rate of reaction. If the forward rate of reaction is favored and both of them have decreased, right? Both of the concentrations decreased, that means that, where should I draw this? I'll draw this over here. That means that this one, they both decreased, but this one decreased more. Wait, no, what? Why did I do that for? Sorry, here we go. Definitely the forward rate of reaction was favored. However, I shouldn't have written them as up and down. It really should be which one has gone down less. So this one has gone down less, and that one has gone down more. Okay, so the forward rate of reaction has gone down less than the reverse rate of reaction, which means that the reverse rate of reaction was more affected by volume change, by volume increase. Okay, if this is more affected, this one must produce less particles. It must produce less particles. Okay. If that reaction produces less particles, we can also look at the stoichiometry and see that that's changed by roughly 2 and that's changed by roughly 1. And so we can say that that's going to be a 1 to 2 ratio for that particular reaction there. Okay, so it is a bit tricky. You need to have a look at it. You have to work out, okay, the spike gives you information about what changed. Then from what changed, you can work out which ones decreased more or less than the other, and therefore you can work out the net rate of reaction. Therefore, you can work out which one is more affected or less affected, and therefore you can work out the number of particles on either side. All right, so lots of information. We'll go through this in class, and you can practice lots. Adios.